So we want to find all discontinuities and tell whether those discontinuities are removable or non-removable. And if you remember, discontinuities occur pretty much where the denominator equals 0 or at the breaking point of a piecewise function and sometimes at the edges of the domain. So we'll talk more about those later. For now, we have 4 examples up here. We have A, B, C, D. Let's just look at part A first. We have y equals 2x cubed plus 5x squared minus 1. What type of function is that?
Cubic.
It's a cubic. But in general, what do we call those?
Polynomials.
We call those polynomials. Polynomials have no restrictions on their domains. And because of that, they have no discontinuities. There's nowhere that the denominator equals 0. There's no possibility for an oscillation. There's no possibility for a jump discontinuity. They are just smooth curves, and they cover from negative infinity to infinity. So a polynomial will always have no discontinuities. So that one's pretty easy. Look at part B. We have f of x equals 5x over x squared minus 9. What type of function is that? Starts with an R. Almost. Rational. Remember that when there are variables in the denominator, we call those rational equations. And we have to be careful with those where the denominator equals 0 because those are restrictions. So let's take a look. 5x over x plus 3, x minus 3. Where are the 2 spots that are restricted? Negative 3 and positive 3. Are those wholes or asymptotes? They're asymptotes. We can tell because they don't cancel, number 1. And number 2, if we plug those numbers in, we get a non-zero number over a 0 number. So like if I plugged in positive 3, I would get 15 over 0. If I plugged in negative 3, I would get negative 15 over 0. A whole will show up as a 0 over 0, not a non-zero number over a 0. So those are both vertical asymptotes. And because of that, we say that they are both what type of discontinuity? Non-removable. Right. Only a whole is removable. Now this guy, part C, is kind of a unique problem. We've been looking at him off and on all semester. We have f of x equals the absolute value of x plus 3 divided by x plus 3. It looks like a rational function, and in some ways it is. It's going to have its problem where the denominator equals 0, which is at negative 3. And it produces a 0 over 0 if we substitute negative 3 in, right? And usually that's a whole, but we learned early on with this type of absolute value function that it turns out not to be a whole, but to be a what? A jump. It turns out to be a jump. It turns out that it forces it to act like a piecewise function, and that's just the nature of absolute value. Depending on whether what's in there is positive or negative, you know, it's treated differently. So if you actually graph this and look at it, over here at negative 3, it'll look like this. And to the right of negative 3, it looks like that. Do you guys remember that? Yes?
Yes.
Okay, so we can always study the graph for these and take a look. So, what type of discontinuity do we call that? Non-removable. So jumps and asymptotes are non-removable discontinuities. And then for part D, we have f of x equals x minus 5 over x squared minus 3x minus 10. What type of function is that? Rational, yeah, it has variables in the denominator. It's a rational equation. We can study those by factoring and see what will simplify and what won't. And we can also see our restrictions better if we factor it. So we have x minus 5 over, this denominator will factor into x minus 5 and x plus 2. So we can see that the two restrictions are 5 and negative 2. Each of those is going to produce a discontinuity there. One of those is removable. Which one? Yeah, it's a whole because you can actually see it I could remove it with algebra. So this one's removable because it's a whole. And -2 is non-removable because it's behaving as a what? Vertical asymptote. Perfect. So most of the time when we discuss continuity, we discuss it on open intervals. But there is a time when you are allowed to say that something is continuous on a closed interval. And it's seen most frequently with square root functions or even root functions. So the definition of continuity on a closed interval states this. A function is continuous on the closed interval from a to b if it is continuous on the open interval from a to b and if the following is true. The limit as x approaches a from the right has to equal the function value of a. So the limit as x approaches a from the right has to equal f of a. And the limit as x approaches b from the left has to equal f of b. It just sounds like a bunch of gobbledygook, but when you see it, it will make sense, I promise. So we're going to look at it in this example. We have f of x equals the square root of 1 minus x squared. What type of function is that? Does anybody know what that graph's going to look like? A semicircle, yeah. Centered at 0, 0 with a radius of 1. So it's going to be really tiny, so I've blown the graph up as much as I can. So we'll look at it. We know that when x is 1 and -1, we get zeros. When x is 0, we get the square root of 1. So it ends up just being this top half of this circle. So let's talk about that graph. It's not continuous from negative infinity to infinity because there's nothing over here. Do you guys see that? There's nothing over there. The domain just doesn't exist over there. The graph doesn't exist, and there's nothing over here. But where it does exist, you can trace the whole thing without lifting your pencil. True or false?
True.
True. Because of that really unique situation, we say that it's continuous on the closed interval from -1 to +1. And the reason we say that is if you approach -1 is your A and +1 is your B here, if we approach -1 from the right, we come this way, that's my limit right there at 0, right? And that's also the function value there. If I plug -1 in, it equals 0. Then if I approach the other endpoint from the left, my limit value from that direction is 0, and that's also the function value. So that's why it's defined so oddly right here. And that's one of the only times we're allowed to say something is continuous on the closed interval. So you will see that most of the time with square roots.